When you're chatting with an AI, it can feel, well, it feels like there's someone home, right? But is there really any understanding going on inside that digital black box? Or are we just getting tricked by some incredibly clever math? And that question, it really gets to the heart of the whole debate. I mean, the common skeptical take is that these models are just fancy parrots, just statistically predicting the next word without getting any of the meaning behind it. But a whole new wave of research is starting to push back on that idea. So you basically have these two camps. On one side, you've got the statistical parrot theory, the idea that the AI is just copying patterns it's seen before. But on the other side, there's this new view that suggests, well, to get so good at predicting the next word, these models actually have to build internal maps of the world. They're forced to develop abilities that look an awful lot like real understanding. So how do we figure out who's right? Well, what if we could actually look inside the model's mind? Turns out we can. There's this new field called mechanistic interpretability, and you can just think of it as AI neuroscience. It gives us the tools to pop the hood, reverse engineer these things, and see what's really going on. So let's do it. Okay, we're going to break this down into 3 levels, starting right at the bottom with the most fundamental piece of the puzzle, how an AI even learns a concept in the first place. So the basic building blocks here are something researchers call features. Now, a feature is just the AI's version of a concept. It's like an internal tag that lets the model know, hey, all these different words and phrases, they're all pointing to the exact same thing. So, for example, to get good at predicting text, a model has to learn that San Francisco's famous landmark and that big orange bridge, and even a photo of the bridge, they all point to one single thing, the Golden Gate Bridge. It basically bundles all those different descriptions under one internal Golden Gate Bridge feature. Okay, so where do all these features live? Well, they're inside something called the latent space. The easiest way to picture this is like a giant, crazy, multi-dimensional map of ideas. Seriously. And on this map, every single feature, whether it's the Golden Gate Bridge or something abstract like justice, is represented by a specific direction. And the AI uses this map in a really cool two-step process. First, you've got the attention layers. Think of them like searchlights, scanning all the text to pinpoint what's relevant. Then you've got the MLP layers, that's multi-layer perceptron, and they're kind of like the model's long-term memory. They take what the searchlight found and connect it to this huge library of knowledge it already has about that feature, and boom, that's how concepts are built and put to use. All right, so if level 1 is all about learning individual concepts, then level 2 is where it gets really interesting. This is about taking those concepts and actually building a model of the world, understanding facts. And to test this, researchers ran this just fascinating experiment. They built an AI called Othello GPT. Now, get this. They trained it only on lists of moves from the game Othello. That's it. It never saw a picture of the board. Nobody ever told it the rules. The big question was, could it actually learn to play a valid game? Now, this is way harder than it sounds. See, Othello isn't like chess. The pieces are constantly flipping color. A piece that was yours 3 moves ago might belong to your opponent now. You can't just memorize sequences of moves. It's impossible. You absolutely have to know the state of the entire board, right now, to make a legal play. Which leads us to the million-dollar question. To pull this off, did Othello GPT have to do more than just match patterns? Did it secretly build an internal, working model of the game board inside its own head? And the answer was a huge, resounding yes. Using those AI neuroscience tools we talked about, these special things called probes, researchers were able to peek inside the model's latent space. And what they found was just amazing. A complete, accurate, dynamic representation of the Othello board, tracking all 64 squares in real time. And the evidence for this was just rock solid. It came down to 3 key things. First, linearity. The model organized the board in a way that was surprisingly simple and clean. We could actually read it. Second, isomorphism. The internal map's geometry literally mirrored the real Othello board's grid. It was a 1-to-1 match. And finally, and this is the kicker, causal efficacy. Researchers could manually go in, flip a piece on the AI's internal board, and the AI's next move would change exactly as you'd expect. It wasn't just watching, it was using this mental model to play the game. But here's a really fascinating twist. This understanding wasn't perfect. In the late stages of the game, when the board was almost full and the possible moves were limited,
The AI would sometimes just ditch its complex world model. It would switch to simpler, more basic shortcuts. It's a total pragmatist. It just uses whatever tool is most efficient for the job at hand. And that actually brings us to the highest level of understanding we're going to talk about. Level 3. This is about moving beyond just facts and models and discovering the underlying principles and rules that govern everything. To get our heads around this, we need to talk about this weird, almost magical phenomenon called grokking. So, a model will be training for a super long time, and it looks like it's just memorizing answers. It seems like it's going nowhere. And then all of a sudden, click. Something just snaps into place. It goes from just memorizing to actually generalizing. It suddenly gains the ability to solve problems it has never, ever seen before. A perfect example of this comes from a simple math problem called modular addition. And don't worry, it's easy to understand. Just think of a clock face. It's math on a circle. So if it's 9 o'clock and you add 5 hours, you don't get 14 o'clock, right? You loop all the way back around to 2 o'clock. So researchers trained an AI on a bunch of these problems, but they never told it the rule. For thousands and thousands of tries, the AI just memorized the answers. Its score on new problems was terrible. And then it grokked. Just like that. Out of absolutely nowhere, it discovered the underlying algorithm all by itself. And instantly, it could solve any modular addition problem with 100% accuracy. It didn't just learn facts, it finally understood the principle. So when you put all this together, what does it actually mean? Well, we're definitely not looking at a simple statistical parrot, but we're not looking at a human mind either. It feels like we're witnessing the emergence of something totally new. What we're seeing is a clear hierarchy, a kind of ladder of AI understanding. It starts at the conceptual level, learning those features we talked about. It then climbs up to build a state-of-the-world model based on facts. And then, at the very top, it can reach a principled understanding by discovering the deep rules that tie it all together. So, the takeaway here is that large language models are not just mimics. They are really building internal structures that, earn the right to be called understanding. But, and this is the key, it's a very alien kind of understanding. It's this strange, pragmatic mix where this deep, world-modeling brain is working right alongside these simple, almost lazy shortcuts. And that leaves us with a pretty profound final thought, doesn't it? We are literally watching a new kind of mind come into being, one that operates on principles that are somehow both familiar and fundamentally alien to our own. It seems the next great challenge isn't just going to be about building these AIs, it's going to be about learning how to understand them.